Welcome, everyone, to Mark Voids a Warranty. Now, I know what y'all came here to see. It's right down here. Oh. Oh, I'm not even on screen. Let's fix that. I'll do another intro here. Welcome, everyone, to Mark Voids a Warranty. Now, I know what y'all came here to see. The Smash Hammer. Oh, yeah. Well, maybe we'll use it today. Maybe we won't. We don't really need it today, but that doesn't mean we won't use it. I mean, it's always all sorts of fun. So welcome. Thank you for joining me. I've got two things for you today. One is the power and logic board from a washing machine that goes along with the dryer that we took down last time. And number two is we're going to take a look at this video card by, is it Gigabyte? Who makes this one? Yeah, I think it's Gigabyte, or at least that's what the sticker on the fan says. So it should be a lot of fun. But before we do, I want to remind you, we're on the drive for 5. That's right. Once we get to 500 viewers, I am taking apart this ridiculously expensive broadcast camera lens. These things are pricey. So I need you to talk to your friends, talk to your neighbors, talk to your friends' neighbors, talk to your neighbors' friends, and get them to subscribe to Mark Voids a Warranty, because I want to take that puppy apart. I've been waiting far too long. It makes me sad, TV land. I just want to take it apart. Break it, please. For me, personal favor, okay? Got a pinky promise? Stamp it. All right. So let's get going. The last Mark Voids a Warranty, we had this bad boy. This is a printed circuit board that had some fire damage. The relay, one of the power relays here, one of the traces on it actually caught fire. And when we looked at it underneath the microscope, which I can bring up for you, you can we're going to have to do a little bit of focusing for you there, I think. Let's see what we can see there. You can actually make out the fiberglass pattern underneath. Now, my best guess is, at the time, and it's still my best guess, is that was caused by a failed solder joint. The resistance eventually grew too high, and a lot of heat was generated at that point, probably melting the solder. Then things just got worse in a hurry. So once that was melted, you then had a spot where electrical energy could arc, and it slowly just burn up the whole copper trace. And that copper trace transferred the energy right down into the board, where it melted the epoxy and the copper all the way back to here. So, fire. For those of you who don't know much about electrical engineering, and I don't expect that everybody here is an electrical engineer, but, you know, there's enough of you that are. For those of you that don't know this, though, electrical engineering, fire is generally bad. Once you let the magic smoke out, the boards just stop working. So, that was a lesson learned here. What could Whirlpool have done better? Maybe better QC, but that comes on their assembly shop or their contract manufacturer, whoever put this board together. I know it wasn't us. That's all I know. So, anyhow, out of that same washer-dryer pair, that wasn't the only part that failed. We also had mechanical failure in the washing machine unit. So I went ahead and took the board out of that too, because I always need more things for Mark Voids a Warranty. And this has a couple things that you don't see too often. One is a board that is soldered at right angles to the first. I mean, you do see that kind of thing in computers, right? You would expect that of a video card to be plugged into a slot and come at 90 degrees. It's one way that you can save space without making things too huge. But you don't often see it. So we're going to take a look at this first, see what there is to see. And then the second thing, and of course we're going to look for other stuff too, but the second thing is these capacitor holders. I don't know that I've ever seen those. Usually when somebody wants to provide a little bit more mechanical strength to a part, they just, you know, cover it in hot glue or epoxy. So we'll see. Anyhow, as we go through this, I do have the chat open. So if you have any questions, I will try to check on that occasionally, and you know, we'll go from there. All right, let's see if we can bring up the overhead. Oh, that's the camera view. This is the one. So I'm looking at this 90-degree connector board, and we've got to get this off. And what it looks like is, and I don't know if you can make this out on camera or not, but it looks like these are tabbed in to these slots. So I suspect if I get these metal brackets out, I can lift them up and out. And once we do that, we can move on and remove the board. It's just attached at 1, 2, 3, 4, 5, 6. So it's attached at 12 joints that are holding it in place, with this metal bracket providing all the mechanical support. Remember that solder doesn't provide a whole lot of mechanical support, so it's usually essential that you find another way to provide mechanical support to your designs. Otherwise, stuff's going to break off over time. So the first thing that we're going to do, oh no, is apply a tiny bit of flux to where we're working. Working at an angle isn't ideal, but if I lift this board up and make it parallel and flat, it's going to take it to be all out of focus for you guys. So this is, I mean, is it an acceptable compromise? I don't know. Yeah, that's not worse. At some point, I will build some autofocus servos for my camera lenses, but that's a project, and I've got a lot of projects right now. All right. For any of my colleagues that are out there that might be watching this, I miss you guys. I hope you're well. And hopefully I'll get to see you at some trade shows here pretty soon. Advanced Assembly front staff is all headed home for 2 weeks while they repave our parking lots. See if we can get this hot enough to melt. I don't know. It's a large thermal mass. Looks like it might be starting to. Might be too much. Okay. It's just a little too much. So what we're going to do is take a little bit of this Chip Quick solder alloy. This is a different metal that, when combined with the solder that's already on here, should theoretically lower the melting temperature and make it easier for me to desolder. And it looks like it is. So let's just keep sucking that stuff up and out. It's a lot of solder. And then they've bent those tabs 90 degrees, so we're going to have to bend them back. That is a lot of solder. My goodness, people. What were y'all doing? Going a little crazy with the solder iron there. Okay, there's one. Same procedure for number 2. I'm going to heat it up. Let's get a little more. There we go. Heat it up and apply a tiny bit of this alloy. That should help transfer heat into the rest, and then it will combine with the solder that's already present And actually, we're going to just do a little trick there. Haha. I don't know if you can tell, but I knocked off a ton of solder just now. Sometimes when you heat stuff up and you give it a quick thwack, a good old-fashioned thump, you can get quite a bit of solder off. Is it good for the board? Certainly not, but we're not putting this back together. Okay. So now that we've done that, let's see if we can suck up some with the solder wick here. Probably could do with a tiny bit more flux too if this doesn't work. And bend. Bend. And then we'll see if we can't heat those up one more time and push them out. I don't know. We'll see. Seems like we have a few viewers joining us. Welcome. Nice to have you here. If you have any questions as we go through, please do ask. Right now we're taking apart a board for a washer made by Whirlpool. Nope, does not want to push out. Okay, well, we'll do this. I am going to cut off those tabs. Now, there we go. So you can see my theory was mostly correct. We've got those 3 tabs that this thing slid into, and then when it was soldered in place, it held it down. So we are making progress. Glorious progress. Okay, we're going to change our procedure here ever so slightly. Before I put the flux on, this seemed to be the way to go. Well, no, let's put flux on. That'll help the heat spread. So tiny bit of flux. Tiny bit of this removal alloy. And then we're going to heat it up to where it's melting and give it a thwack. Just to get as much of that off as I can. Now, oh, that didn't get hardly any for me that time. So now that we've got that off, it's time to hit it with the solder braid. And I'm using a nice thick one here because we've got a big fat joint with quite a bit of solder in it, and we want all that solder out. Since there's a high level of adhesion from solder metal to copper, it soaks it up. It's called wicking. And it's the same thing that helps your paper towels to work. So there's one. Now we'll do number 2. Tiny bit more flux because I saw that all burn away. And while I'm doing this, you know what would be handy? Would be a voice-controlled soldering iron where you could just tell it to reset the temperature for you. Oh, that'd be fancy. I don't know how useful it would be, but it would be cool. So get on that, internet. Come on. Let's see how we did there. And then last time, the thing that seemed to work for us was just clipping those tabs right off. that away from myself, so if it snaps. Now, not the most elegant way there. I'm just mark smashing right now. Come on, get out of there. There's a lot of solder left in one of those, in that bottom hole. There we go. Not anymore. Okay, now all that's left are these little joints connecting the two boards. So if you ever had to do something like this in one of your designs, I would actually recommend using some bigger traces if you can. Bigger holes, bigger traces. I don't know that I would put everything. Not that those things are too small, but personally I would go a little bigger if you could. Just give yourself a little more flexibility. Oh, should have pulled that and cleaned it. So you might be able to see just how much solder this is able to wick up. It's quite a bit. It does a good job. And I'm just trying to pull it all out of those fillets there, so that there's none left behind. Might be easier to see if I put it down angle. So I just worked on the top side there, and I'm going to work on the bottom. Flux helps clean joints. It also lowers the surface tension of solder, and it also allows heat to flow just a little easier. All right. Making progress. Not a lot of progress, but we're making progress. And then over here, doing the same thing. A little bit of flux. Little bit of heat, little bit of solder wick. All right. Once we get this off, we'll be able to get a better look at each board and see what it is that we can learn from them. There's most of the solder off one side, and there's still quite a bit left, but if I was worried about putting these back together, I would do a more thorough cleaning job. It wouldn't take long. But since I'm not, and your time is valuable, we're just going for speed here, not quality. Okay. We're going to zoom out for what I'm going to do next. So, Christian, if you're watching, this is going to be your favorite part. And just so you can see the unbridled joy on my face as I do this, let's get over to one of these dual cams here. Okay, here we go, buddy. No. I think Mark needs to smash more. It's loose. It's certainly loose. It wants to come out. Okay, I gotta go to the edge of the desk here. Sorry, peeps. You'll just have to appreciate that I am hitting it. I just can't show you. There we go. By the way, that is not an approved rework method. We frown on that at AA. Good thing I'm not at AA. All right. So now we've got our two boards out and free. So yay us. That's exciting, huh? So they've split the board into power conversion and regulation. That's this one right here. And the way that it looks like it goes is they bring the power in on one side and run it through one of these two transformers. I'm not really quite sure which. Two diodes over here. If this is all they're doing, they're just pulling half-wave rectification. There are two more over here, but it's odd that you would see a little rectifier bridge that would be spread that far apart. It's possible. I'd have to look at the traces a little closer. Then we've got some big fat reservoir caps. Some IC. I can't make out the top side markings without looking through the microscope there. And some more caps. Looks like a FET of some sort. And then the power comes out down over here. So that's pretty cool. That's a pretty decent layout. It'd be nice if I knew a little bit more about the design and why they chose to do a few things that they did. Like here you can see a via array that I don't know what purpose it serves, to be honest with you. It looks like they're trying to connect the copper pore up top to the copper pore on bottom, and that's great, but they could have done it with far fewer vias. I'm not really sure why they did that. I've got no objections to it. It doesn't really cost that much more money, and it's not a big deal. It's just interesting. So, on the bottom side, you see a lot of these copper pores were left uncovered. There's no solder mask protecting them. Well, you can't leave copper exposed because over time it will oxidize and degrade. So it looks like they used a tin surface finish. Now, it could be that this is all solder that was deposited in a wave reflow. So, you know, they put all the parts on the top and then they send it through a reflow machine. And it sure would make sense based on where all of these blobs are that it went through this direction first and it came out that side. So, well, that's interesting. We'll look at that under the microscope in a minute. Now, the second thing that we've got is the other part of the board. This one has, you know, a series of relays which probably run different things, you know, solenoids or maybe motors. I don't really know right off. We'd have to know what they're connected to get a better idea. But my suspicion is that those 4 relays correspond to these 4 connectors. And those are actually the only board connectors that I see on this. Board connectors are expensive, so instead they've gone edge connector. Now, oftentimes you'll see this and designers will do a gold plating. You know, a hard gold plating because gold doesn't oxidize. But on something like this where nobody's ever going to see it, you don't really expect that many insertions and removals. They just felt that they could get away with the, you know, a hassle or tin covering. I mean, that's totally legitimate, except that this can still oxidize. It can still give you a bad connection. So if you don't have enough wetting current to break through any oxidation, wetting current, minimum current, right? Minimum voltage and current needed to go to break through and make the connection to the rest of the circuit, you end up with fires and stuff. So on low voltage, low current things, you're pretty much stuck to an oxide-free finish, right? So that means you got to use gold. But something like this, heavy currents, maybe you're running 10 amps through something. I doubt they're using that much, but let's say you are. That becomes valuable. So with that, I think it's time that we flip over to the microscope and see what there is to see. You guys have any questions as we go? Please let me know. And I have plenty of time to make more rhymes. Oh yeah. All right. Microscope, here we come. Give me just a moment and we'll get you focused in here. Once I figure out which way to go. Lower. All right. So what I'm looking at here is just this is the big board, the one that has the microcontroller on it, and looks like the one that they're using here. Oh, I don't know if I recognize that. I do not. Sorry that it's upside down, but it says something along the lines of MC908AP64. And I really don't recognize that logo, but I'm sure some of you out there do, so let me know if you know. So this is whatever microcontroller that they've decided to use. Usually what you want to see in something like that is decoupling capacitors that are, right on top of it, and I'm not seeing any. There's one. Why maybe that's a decoupling cap. I don't see any ties to power and ground. Is that a cap? If it is, that's poor layout practice. There's maybe one? Yeah, that's got to be one. But where's the tie back to VCC? This is confusing. Whatever it is, I don't like it. So you have this issue called ground bounce. And with ground bounce, there's these little, inside this big old package, there's a little silicone die that's, a fraction of the size. And there's all these gold wires that connect the silicone die to the metal lead frame. Anytime that you have one of those pins flip, logic states, well, the path from the die through that bond wire to the lead frame, from the lead frame to the cap, and back again creates a huge inductor, right? It's this big loop, or big enough. So if you have a very fast switch time inductor, you get a large induced voltage that shifts the ground potential of the die from the ground potential of the board. They have different reference potentials, and therefore, different voltages. You can actually induce a current. It happens on the high side switching and the low side switching as well. It's just usually only an issue with ground as you shift the logic levels up. So logic levels drift during pin switching. Pretty complicated. I got a paper on it if you're interested. Email me, mhughes@aapcb.com. I'll just send it to you. So the way that you get around that is providing low inductance return paths. You want to get your capacitors as close as you can without getting yourself into trouble, right? You still have to respect courtyards. But you want to get these things as close as you can, and you want to make sure that the ground loop is as small as possible. So assuming that this is one of the VCC pins, and this is one of your decoupling capacitors. Okay, So VCC to here, I guess, but where's the other side of this going? Oh, gosh. I don't even know where the return is. Maybe if we flip it over, we'll know a little more. Nah, I don't think so. But it's just not a good practice. So always put your decoupling caps as close as you can. You know, you don't have to violate courtyards, not that close, but close enough that you have a low inductance return path for those things. So let's see what else there is to see. So we've got a few vias here. You can kind of see how the drills tend to not always be centered. That's typical on designs. One thing I like that they did here, you know, you've got a via and then it comes out and, you know, you get this Y joint. If this drill fails in this direction, right, along this trace, well, it could interrupt that connection. So if you would have if they would have teardropped this or keyholed it, that would have decreased the risk. That would have been great. They didn't, but they did move the via out to off to the side. Now, the reason you want to do that versus putting it in the middle and running your traces to it, if ever you can, is if the drill wanders to the right or the drill wanders down, it can disrupt that net. Here, there's only one direction the drill can wander to cause a failure. Here, there are two. So by doing it this way, you've actually decreased the likelihood of a failure. Manufacturing has, it's not perfect. It's got fluctuations. So anytime you can make your life a little safer, you should. Right here you can see this one's clearly not centered. It's not off by much. They did a good job on the fab. But it is off. And if it goes off in the wrong direction, you're out of luck. So use teardrops whenever you can. It's always good practice. Use vias so that if the if the drill does wander, you don't break your net. So don't do that. That's a mark no bueno. For those of you out there who don't speak Spanish, no bueno is the opposite of bueno. Every day, learn something new, right? All right, I'm just looking around to see if anything else catches my eye. Multiple vias whenever you can to tie ground connections together. That's always a good thing. Or any copper pores, any high current traces. Use multiple vias. It lowers the inductance and gives you a better chance of success. Looks like I knocked our focus a little. Sorry about that. These are the board edge connectors, and you can see that hassle surface finish. Blech, yucky. Pay for enig or any pig. So just looking around, seeing what there is to see. Looks like there's some LPI that got in that hole, or flux or schmutz or something. This one looks like it's tinted on the back side. I don't know what happened there. Maybe it inadvertently tinted on the front. It is nice to keep your copper covered whenever you can. Our LPI can actually tint holes much larger than this. Looks like there's schmutz left on the board. Never a good call. Always want to pay to wash your boards too. Here we go. This is what I was talking about. So with this via, let's see where right? This via can drift in any direction, right? The drill can wander in any direction, and it's not going to be a problem. There's no direction that if this breaks out, there's no direction this hole can go that this trace and net won't still be just fine. It can go down all the way. It could break out 180 degrees. This would still work. So anyways, that's the better way to go when you're connecting things, when you're adding traces. to vias. Just resistors. Got a big fat trace. Oh, that's interesting. Why did they step that down? I couldn't tell you. I don't know if they could tell you. Why? So here's what they necked down this trace in this little area. And I don't know why. Maybe they do, maybe they don't. I don't know. All right, well, I think we've seen about everything that we want to see on this board. Bottom side isn't that spectacular. A lot of the same. It looks like we've got plenty of test points so they can tap and test every one of these nets. You know, using a flying probe or a bed of nails. But looks like a lot of those vias, their whole purpose is just to provide test points. So whenever you do this, it always is a good idea to put all your test points on one side if you're using a bed of nails fixture. If you do that, then your costs are going to go down because you don't have to have wire harnesses coming from above and below. You can just make a, gosh, I'm blanking right now. But you can just make a test fixture that's much cheaper. So, Whirlpool. So here is the other board. This is the power control board. Looks like they do have some vias, but everything here has been filled as it went through the wave solder or the selective solder machine. Again, you've got this array of vias. I'm not really certain what the purpose of having so many is, but a lot of, you know, this board was built probably 2010-ish, maybe a little earlier. So you still have quite a few plated through hole parts. These would probably be, unless they needed it for high voltage, you know, creepage clearance concerns, these things would probably be surface mount now. ICs are almost all surface mount now. ST Micro VT per something. Looks like it got something on it or cleared away. Nothing too spectacular here. Just a typical power control board. I do like that, and we can switch back to an overhead view here. I wonder if we can get in a little more. I do like that they put everything on one side, so this thing could just go, go through on a wave reflow once. You don't have to repopulate and put on new boards or attach anything by hand. So it's good. No real complaints. You can see plenty of spacing between nets of different potential, right? That big gap there is to prevent, what's it called? Carbonization and creating electric currents that go from one potential difference to another, or CAF, conductive anodic filament failures. So, all right, that was fun. Next up, we've got a video card. So different types of design engineering here. Here, power is one specialty, high speed is another. Video cards have to communicate a lot of information. Depending on the resolution, the refresh rate, the color mode, it can be an absolute ton. Even 640 by 480, 8-bit is a ton of information. And that is, the lowest resolution that's out there. Well, that's not necessarily true, but it's one of the, probably the lowest that people typically still consider to be video, till you get some tiny little stuff. But anyhow, you've got to convey a lot of information quickly. The way that you typically do it these days are with differential pairs, at least from board to board. All right, so all I've done right now is just remove the end connector, and then I'm going to see if I can get that heat sink off, which looks to be these four. And what we've got here are some spring-loaded screws that I suspect keep that drawn tight and give it a little bit of play. All right, let's see what that does for us. Okay, so that releases a custom fan assembly. Let's see how this holds on. And all this guy does is you've got a fan that blows air into these fins. So heat enters here and probably through this stuff as well. Heats up this big center block acts as a huge sink. The thermal energy then travels along these fins as it spreads out. Fan blows and the air conducts it through these channels out and away into the environment. So it's pretty substantial. It's kind of interesting that the fan is, I don't think I've seen a fan like that, shrouded and built, screwed right onto the board. That's interesting. So anyhow, now we've got the board. So video card, we've got a main central bit of silicone. Looks like these are the memory blocks. Everything else is likely support circuitry for that stuff. Power regulation and control. Looks like we've got, I'm sure there's, is it all just power here? Maybe. And then signals running everywhere. We'll look at those in just a sec. Looks like a clean enough layout. And then a ton of components on the backside. I mean, this must be a nightmare to design and keep track of the bombs. I wonder how they're even making these right now in the era of the silicone shortage. It's really hard to get a hold of parts. And the bigger your bomb, the greater the chance of you running into trouble. So what do you do for something like that? I don't really know. Let's take a look, see what there is to see. All right, so this is the main chip. It's covered in goop. We don't really know what it is, but it is a chip that has been connected to the board. This whole green thing is, and you know, it's got a few 010-005 passives, and you can make out one or two. They look like traces. I don't know that they are. They might be. Or it could just be separations of copper pore. But anyhow, that big old green thing then breaks out to the rest of the board. And you can make, as you look around, the various differential traces. Let's see if I can get a pointer here. So a differential trace is two sets of wires. And one of them will go positive as the other one goes negative. So you have, you know, whenever this is a plus signal, this one will be minus. Whenever this one's a minus, this will be plus. Now, the reason that you do that and you send them both down at the same time is if they pick up any interference, both of the wires will pick up the same amount of interference. So by looking at the difference between the two logic levels, you can basically You can subtract. You know, if one's higher than the other, it's logic one way. If one's lower than the other, it's logic the other. So it helps defeat interference. But something people don't often remember, though, that they screw up, is they think that the signals in one will cancel out signals in the other. Dude, in a perfect world, in a theoretical world, sure. Yeah, a little bit. But the issue that you often have is that these trace lengths are different, right? It's like runners going around a track. This guy on the outside trace has longer to travel. It's going to be slower. So these signals aren't going to be perfectly synced all the time. So really what you need to do is make sure you're coupling to an adjacent layer. That's how you do it. So these guys come out and then they go relatively quickly down into a lower layer of the board. Come out, lower layer of the board, lower layer of the board. Here they did a little bit of length matching. That's what these meanders are. And the whole goal there is to try to keep these things in sync so that by the time you get to the other end of the trace, wherever that other end is, that the signals arrive here at the exact same time. I don't know that it always happens. And sometimes I think engineers spend too much time trying to make it happen when they don't necessarily need to. You know, there's a little bit of fudge factor given in your budgets there. So, got a ton of vias connecting things, and that is something I always like to see. So, you know, if you've got a power trace or something like that, and it needs to run to other layers in the board, run a bunch of vias. Make sure you've got plenty of low impedance paths to go there. And that's, you know, looks like they did that in spades. They went a little nuts. You don't want to put too many vias too close together. You need to talk to your fabricator first. See what their minimum pitch is, the between vias. I'm sure these are fine, but sometimes people get a little too crazy and one drill can just kind of fall into the other. You don't want to do that. That makes them sad. It'll depend on the drill diameter and what your fabricator is going to allow. So here we've got a ton in rectangular patterns, and my suspicion is if we were able to flip over the board accurately, on the other side of this we would find an IC maybe. Ooh, it's hard. There's too much stuff here for me to know what I'm looking at exactly without some careful measurement. But I'm guessing this is it here. This looks like a MOSFET of some sort. We could look up the top side markings and know for sure, but I'm guessing they're just using that as some thermal conductivity. Just a nice non-plated through hole. They've pulled the copper back from... Did they? What did they do here? Is that epoxy? Just filth that's giving me a bad perception? Maybe. Looks like it's misaligned a little, whatever it is. Is that a via? What is that down there? That's weird. All sorts of interesting stuff. By the way, if you have questions, I'm happy to answer them. Anyhow, back over here. So, memory is going to be connected with a few different channels. Odd that they decided they didn't need to meander any of these, but they meandered the others. But basically for each memory block, you know, if it's 16-bit, 18-bit, you'll get 16 or 18 wires. Sometimes there'll be differential pairs, but parallel is fine. So you just load up your data signals on each one of these, and then you have a clock that clicks over and says, okay, it's time to read those things and see what they are. All right. Well, anything else here that's interesting? like I said, I like the fact that they're using multiple vias to stitch stuff together wherever they can. That is a good call. You never know when you're going to have trouble with one, or it ends up being a higher impedance than you think it is. Let's look at some differential pairs and see if they did some ground returns. That's always a common mistake. Let's see if we have any of these going to vias. Nope. Meanders, meanders, meanders. Okay, here we go. This is what I was looking for. So one of the things that designers often forget, whenever you have vias, a differential pair, high-speed differential pair going into a board, a lot of times they know that they have to have a return path, and that return path is going to be on an adjacent layer of copper. What they don't remember to do is come up with vertical return paths. So as these vias plunge into the board here, how is the signal going to go from the layer below it to whatever other layer it needs to go to? Well, it's with these vias right here. These are ground return vias. Now, I don't know that they're laid out perfectly, but there's probably reason for that. If we look on the other side, it was covered in components. I mean, they probably just did the best they could. But each one of these vias, you know, as the signal goes down, it can use this via to come up, for the return to come up. As this signal goes down, it can use this via as the return to come up. Now, if you can put in the vias, a few more vias, would that be better? Of course. But you do what you can. At least they did it, right? That's something that you see people forgetting all the dang time. Here's something else that's kind of interesting. So they did vias on the surrounding this non-plated through hole. And I suspect they did that just to help tie everything together, tie the layers. They thought they were tying the layers stacked together. That would be my guess. Now, if you go over to the other side of this board, it is just covered in stuff. There are parts everywhere. They're going a little overkill with the vias that they're using for thermal conductivity. You don't necessarily need that many. They probably didn't know exactly how many they needed, so they went a little over to be safe. You know, better to be safe than sorry. And this is just a ton of components. You've got capacitors, filter capacitors, reservoir capacitors. These things are all decoupling the other side of the board. So, all right. Well, that is probably all I see there. I know it wasn't... Oh, which camera do we want? There we go. I know this wasn't a complete teardown, but I've had these boards sitting around a little while. I figured heading into the long Labor Day weekend, we might have a little bit lower viewership. Might be a good time just to knock these things out before we tear apart a full product again next week. Well, before I go, do you guys have any questions? At least one question. You all are real quiet today. Makes me suspicious. No? All right. Well, I certainly do appreciate you joining me this time for Mark Voids a Warranty. Next week, we're going to take apart something bigger and something complete. But before I do, I just wanted to run this past you. I've been working on another channel, still trying to figure out what it's going to look like, called Mark Makes a Mess. And in that, I've got some projects that I can do. For example, we can use a Structure Core 3D scanning module, look and see what that's all about. We've got a little phased radar array we can play with. A lot of different things, but I need to know what's interesting to you. What would be valuable to you? What would encourage you to watch? Let me know. Send me an email, leave me a comment below, whatever you think is useful. And I'll try to head in that direction. Well, thank you for joining me on your lunch. It's always fun to have something to take apart and learn a little something from, and hopefully see something new. Like this time, when have you ever seen one board, married to another that way? You don't, or at least I don't. So that was kind of interesting. That was kind of neat to see. Maybe that's something you can use in your designs. I don't know. Well, thank you. As always, if you ever have any board requests, questions, comments, you want a webinar, anything, shoot me an email, mhughes@aapcb.com. Or if that's too hard to remember, just email sales@aapcb.com and they'll get in contact with me and we'll make your life better. So, thank you so much, everyone. I hope you have a great long weekend and safe and happy week. And I'll see you all next Friday.